the science and rocket science. We're going to talk about payload. So let's take off our engineer hat for a second. Let's forget we have rocket fever and all we want to do is just see a rocket launch and think, what is the point of doing any of this? Number one, rockets are expensive. Number two, rockets are dangerous, as we've covered. Number three, rockets are work intensive. Rockets of this type have been launched for almost 100 years. Spoiler alert, this is a well-covered area of rocketry. There's not much left to discover in this field. I mean, there's always stuff, but like, it's a well-developed field, right? We're not on the cutting edge or anything by doing this type of stuff. And we can't even reach space with our type of rocket, so why are we doing it? It's all worth it if we're doing science. The reason we're here and spending all this money and time is to do science, okay? And like, this is something like I like to harp on because I'm trained in physics, not in engineering yet. I was on the team, so I'd always love to yell at the engineers and be like, no, you don't get it. It's all worth it if we're doing science. The payload. So remember, spaceport requires all rockets to contain a scientific experiment, aka payload. Payload is a generic term that can mean anything. You know, cargo, if you're talking in military weapons. But in the aerospace community, at least with ISS, with what I work with, payload equals science. They're ubiquitous. Rules the competition gives us about the payload. The payload must be self-contained and cannot influence the flight in any way. The payload must weigh at least 10 pounds. And there can be no toxic materials, lead, or vertebrates in the payload. So vertebrates is anything with a spine. We can't have invertebrates and plants. That's fine. And cells. And there's other rules, but those are the big ones. So I'm going to tell you guys just kind of a little bit of an experience I had with a professional rocket science payload. So we're going to talk about UH2 obviously, but like I got the blessing to be able to talk with a research team when I visited Alaska last year that was doing rocket science, like cutting edge aurora physics in rockets. They're called the LAMP mission, and I'm going to tell you about kind of what they did to have a successful mission, and if you want to continue this throughout your career and do science on board rockets, kind of what you need to do and what example you should follow. So LAMP stands for Lost Through Auroral Microburst Pulsations. This was a project commissioned by NASA Goddard, and basically they shot a rocket into an active aurora up in Alaska. So I was there doing other research with UH, not rocket stuff, but my professor knew the professor who was doing this, and we got to meet the team, and it was really, really awesome. And their lunch happened while I was there. So this is actually posted in a bar I went to just to eat lunch. It was like on a board next to, you know, like loader, dock workers wanted to call this number next over, be a citizen rocket science, tell us about auroras you see. So they were studying a specific aurora phenomenon called microburst pulsations. So I'm gonna tell you about the aurora stuff because it's so cool, and like that's part of my area of research is plasma physics. My professor, Dr. Bang, I talked to you guys about before. He's the only professor at UH who was an active rocket scientist. His career was covering radio emissions generated by Earth's magnetic fields and auroras. So that is partially what the LAMP mission was studying, and I just think this is so cool, so I'm going to play this for you guys. What this video is a compilation of different radio phenomena generated by the Earth and other planets. So any planet with an active magnetic field and plasma is going to generate these radio emissions, and it's just from properties of the plasma, like doing weird stuff. And if you scale those radio emissions down to what you hear in your ears, like, you know, you're in a car, your car antenna picks up radio frequencies, translates that down into audible stuff you can hear. This is what it sounds like. It's really cool.
Earth whistlers.
So whistlers. So this is something that was really explored in the 70s. This is something that they first discovered in World War II. I'm gonna pause here. Where soldiers who were deployed and using some of the first long distance radios heard these things on their radios, and they're like, what is that? What the frick is on my radio right now? They said it sounded like grenades whistling over the heads of the people they were talking to, hence whistlers. What they actually are is lightning strikes, generating large electric and magnetic fields in the atmosphere and creating these transitions.
Multi-hop whistle. Earth, proton whistlers.
Another aspect of whistlers is generated by protons. So there's a bunch of these in here, so I'm gonna skip around as well. There's many radio emissions that Earth's atmosphere makes just because it's a magnetic planet. One of these is the chorus. This is due to the Van Allen radiation belts. And check it out, this was first observed on a satellite orbiting Earth. There's auroral kilometric radiation. This is something that occurs right in areas where aurora is active. Oh, and this is probably my freaking favorite. So like I mentioned, any planet with a magnetic field can generate these. This was found on Jupiter by Voyager 1. So these are lightning strikes on Jupiter that it was able to listen to.
Jovian chorus.
Just like us, Jupiter has a chorus. So this is basic, well, I don't know how much I want to talk about the physics. There's a lot of cool space sounds and it's all generated by upper atmosphere. The fact that it's you have a magnetic field up there. Anyway, that is was a huge part of rocket science in the 70s. Like there's a whole rocket range up in Alaska that I got to visit. The whole point is just launching rockets into the aurora and seeing what they can find. So I'm gonna talk a little bit specifically more about LAMP. So this is kind of hosted out of Goddard, kind of hosted out of the University of Iowa. Their goal is to explore the energy of a certain type of aurora called pulsating aurora, like I said. And we'll look at a video of it later. The LAMP rocket seeks to understand the energy range of electrons that cause pulsating aurora by launching into an active pulsating aurora event, measuring the particles and fields in that region. Why did I read that aloud? Because it is a clear, concise explanation of what they're doing, what they're measuring, and why they need to launch a rocket to do it, right? They know exactly what they want to measure, exactly the fields they're looking at, exactly what their instrument needs to do, and that exactly where the rocket needs to go to see it. Okay, I'm gonna go to their instrumentation page just to talk about some of the things they slapped into their rocket. So first, this is one of those probes looking for the energy of the particles they're looking for. So this is a lot of radio frequency and then like electrical engineering type stuff to get a survey of the particles up there. They also put a fancy camera in there. Check it out, it's circular. Why is it circular? Because that fits into a coupler going inside the rocket. They also have a high energy particle detector they flew on there, a magnetometer which measures the magnetic field, and I don't even know what this is. Solid state detector scale telescope observing electrons from energies 3 kiloelectron volts to 2 mega electron volts. So they've actually flew a lot of instruments that measured a lot of different things, but each of them had a purpose because they knew they wanted to figure out more stuff about pulsating auroras. Going one more page to their objectives. What is the optical signature of the auroral microburst precipitation? That's why they had the camera, optical. Do these microbursts account for high frequency modulations typically superimposed on the pulsating aurora? So do the microburst precipitation of particles correspond to that visual thing they see? Last one I don't understand what they're saying, but they have very clear objectives, very clear science laid out on what they want to do and instruments to do that. And they have a video of their launch. So at the front here, we're going to look at what a pulsating aurora looks like. So you see that bright band that just popped up there? It's very catchy. learned in Alaska is that there's just like so many types of aurora. Like it's not just like it's there as one thing and then gone. It's a fluid. It's a magnetized fluid, a plasma. So it looks almost like smoke, right? Smoke can do a lot of different weird things. It's really cool. So I'm gonna skip right to their launch, which is about 2 minutes. Yeah.
There it is! Get your shutter, sorry, they didn't count that down. Allie, you saw a rocket! That's the second stage audio.
So something you noticed there, you saw the light first before the audio reached them, proving the speed of light is faster than the speed of sound. There you go, there's your proof. So cool. So that's active rocket science. That's what's like the cutting edge professional science in this type of rocket. Okay, so group, what did the lab team do to have a successfully executed experiment? Set an objective. What do they want to study? Good.
No, they put in instruments that can measure things.
Put in instruments, yes. And specific instruments, like attuned specifically to what they wanted to measure at that altitude and at that occurrence, yes.
Tested things so they made sure it worked.
Yeah, they tested things so they made sure they worked. Very good. Those are all good ones. So clear specific scientific questions, built experiment off of the work of other experts in the field, robust instrumentation goes back to testing, demonstrated that their research advanced their field of study and they needed to use a rocket to get the data they wanted. So something that's hard for teams at spaceport is like, you know, I can come up with an experiment, but like it doesn't need to be in a rocket, right? Because the thing about a rocket, like you can generate a high G environment in your car. You can drive and slam on the brakes, and if all your experiment needs is like high Gs, like you could do something like that. You could do a spinny table. Like there's a million ways to generate high Gs that don't require an expensive fancy rocket. So finding a mandate to use a rocket is actually kind of a tricky task. You need to do something that only can happen in a rocket. And in this case, the only thing they could do is a rocket to get to the upper atmosphere because it was too low for satellites to fly, but too high for us to reach in like an airplane. All right, now let's talk more about our team and what we do here. So our team's science objectives have focused on how rocket flight influences biology. This is great because NASA Johnson Space Center, where I work and what we're right next to, is the center of human spaceflight in the entire world. So there's a huge community of people looking at how space high Gs affect the human body. So in 2019, our payload was looking at how soft tissue like the brain is affected by high G accelerations. I think in that case, our brain matter was like egg whites. Engineers made that experiment. 2020 to 2022, we've looked at how reproduction rates of bacteria change during rocket flight. And then coming up this year, I don't know if you guys already know this, but this is a hint of what we're doing this year. Does anyone know what our science objective is right now?
So, we were looking to a payload either food flight or and how those react in
Yeah, so that's really good. So I base this off the statement of work that I got from Joe and Robbie. Basically, the idea is that they're going to take fruit flies or fireflies, some sort of insect species, and freeze them as if they're going into cryosleep for a deep space flight. So what if you launched people or creatures in cryosleep, what would happen to their body? And I don't know exactly how they're going to quantify that. Maybe Izzy has more information.
Yeah, so the mission to Mars, one thing that they're working on is torpor-inducing habitats to transport humans to Mars. It's about an 8-month resources are these like kind of cryosleep chambers. So they lower their body temperatures in order to put them into like a hibernation. So that's on the bigger scale of what NASA's doing, is they're working on that. We're doing it on a smaller scale. We're taking fruit flies. They share a little over like 60% of their genome with humans, so we can directly correlate a lot of genes between us. And we're trying to lower their basal body temperature enough to put them into a state of hibernation and see if that is a neuroprotectant when we launch them. So it should help like brain signals survive, their spines, a lot of like CNS stuff, and then as well as like hopefully the flow to the rest of their body.
Thank you. Yeah, so that's what we're doing this year.